Yes. Yeah. No, it's not acting as a base.
You're only going slowly.
Okay, this is an aside. An aside is like this. You know, if ammonium is present, so shouldn't I do Ka for ammonium? And ammonium is going to hydrolyze water. You know, acids hydrolyze water. They're going to be a proton donor. I'm going to form ammonia plus hydronium. And so here I'm going to have 1.8 times 10 to the minus 5. And so should I worry about the ammonium? Yes or no? This Ka.
Yes. It's also a contributor of hydroxide. Like if it contributes hydronium, then
then that should cancel out some hydroxide, right? If I generate some hydronium, doesn't that cancel out some of the hydroxide I just generated and change the pH?
Mm-hmm.
Yes or no?
Yeah.
The answer is, and this is why it's tricky, the answer is no. I don't have to worry about this. And you might ask, why don't you have to worry about this? Well, that's not the reason. A lot of people, I ask people, why don't I have to worry about this on tests, on past tests? And a lot of people will say it's a small number. But that's not the answer.
Bigger than mine.
Yeah, this is bigger than 10 to the minus 7. You know, and well, anyway, the reason is because of this. This equilibrium describes the equilibrium between ammonia and ammonium. And so if I have this much ammonium, I also have this much ammonia, right? This came from there. And this is going to be 0 here. And so what we see is this describes equilibria between ammonium and ammonia in terms of pH. This describes the equilibria between ammonia and ammonium in terms of pOH. And so the only difference is this. This is redundant because we just did this equilibrium. The only difference is we'll get the pOH in that case versus the pH in this case, but they're going to be the exact same, right? In terms of pH. And so this would be redundant. We already described this equilibria here. And so this is what you have to think. For base solutions, we only look at the hydroxide ion contributors, because if we start looking at each hydronium ion contributor, it's going to be redundant. All of a sudden, we're trying to shift. Well, in one case, we're looking at pOH, 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 and then all of a sudden we jump to pH and then back to pOH. It doesn't work that way. We got to stick with pOH, 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 and then figure out the pH depending on the final pOH, right? And so here, for base solutions, only hydroxide contributors. For acids, only hydronium contributors. Let me give you an example of this here. I didn't talk about this earlier because I didn't want to confuse too many people, but an example would be phosphoric acid. H3PO4 hydrolyzes water, H2O liquid, to form hydronium plus H2PO4 minus. H2PO4 minus is both an acid and a base. This is amphoteric. If it's amphoteric, then what should I do? If this is my step 1, for step 2, should I go Ka or should I go Kb? Or both?
Uh-oh.
Ka and Kb.
Okay.
We only do Ka because you know what Kb would be? Kb would be step 1. Kb would be step 1, same as step 1, except for POH. But you know, POH and pH have a seesaw relationship. And so it's redundant. And so this is why when we do something like this, we always look for the Kas. When we do bases, we always look for the Kbs, Kw,
Is there any case where we'll have to do both?
Yes. There is a case where we have to do both. And that's, the case where we have to do both is when there's no step 1 present. Okay, and let me explain what I mean by that.
Good question.
And so the answer is, this is it, and we completely ignore that, right? Okay, you must do both. If there was no step 1 present here, and when no step 1 is present is like a sodium dihydrogen phosphate solution, 0.100 molar. And so here, there's no phosphoric acid present, so we don't have that step 1, right? We're just dealing with dihydrogen phosphate. So when we look at this, you know, this is soluble salt. And so if you want to do the first step, we don't have to do it like this, but I'm going to do it like this. The first step is a soluble salt is a strong electrolyte. Strong electrolytes ionize completely. And so this is going to form sodium ions and dihydrogen phosphate. And so initially I have 0.100 molar here, and I'm going to assume nothing's ionized, so it's 0, 0. And so the change, K is going to be very large for this because strong electrolytes should be very large. So this is going to be going to 0, this is 0.100, this is 0.100. And so there's no phosphoric acid present here, no H3PO4. And so what do I do? Well, H2PO4 minus, now I got a choice. Do I do Ka for step 2? Or should I do Kb for step 2? And so what is the Ka? Well, the Ka is going to be H2PO4 minus is acting as an acid. And so when it acts as an acid in hydrolyzed water, we're going to form hydronium and HPO4 2 minus. So this is my Ka. The Kb for this is when H2PO4 minus hydrolyzes water to form hydroxide and H3PO4. The reason we could ignore this in the previous is because this is the equilibrium between dihydrogen phosphate and phosphoric acid in terms of POH. If you look at step 1 was the equilibrium between phosphoric acid and dihydrogen phosphate in terms of pH. This is redundant, right? We don't need to do it. This one, though, well, look at our step 1. It's not redundant at all. Both of these are unique, and both of these are going to generate unique species. Do you see that? And so we have to do both. We must do both.
Must do both.
Yeah. Must do both. And so which one should we do first? Should we do Ka or should we do Kb? Well, probably we should do the one with the larger K. And so let's look at the Ka for this. The Ka for this was what, 6 point times 10 to the minus, somebody remind me, 6.3 times 10 to the minus 8 or something like that? This is Ka2 for phosphoric acid. I don't want to use the one on the chart because one on the chart doesn't match our book.
That's right. For phosphoric acid.
Is it right? Okay. So now we need Kb. This is Kb for dihydrogen phosphate. So Kb for dihydrogen phosphate is equal to Kw divided by Ka for, what's the conjugate acid of dihydrogen phosphate? What is the conjugate acid? Dihydrogen phosphate. Phosphoric acid, HCPO4. And so this would be 1.0 times 10 to the negative 14 divided by
6.3 times 10 to the negative.
no. Phosphoric was higher.
7.1 times 10 to the negative 3.
7.1 times 10 to the negative 3, which gives us a Kb of
1.48 times 10 to the negative 12.
We'll just carry one extra digit. 1.40 times 10 to the negative 12. So which one should we do first? We should do K8 first. Let's do that.
Why?
This is bigger K. Bigger K. We just always do the bigger K first. All right, so let's do the bigger K first. So we're doing H2PO4 minus plus H2O liquid. We're going to produce hydronium plus monohydrogen phosphate. So initial amount here is 0.100 molar. The water, we ignore hydronium, 0 molar, 0 molar. So we're assuming nothing's happened yet. Okay, so the change is going to be minus X molar, plus X molar, plus X molar. So at equilibrium, we got 0.100 minus X molar, X molar, and X molar. So Kb is going to equal the hydronium ion concentration times the monohydrogen phosphate concentration divided by the dihydrogen phosphate concentration, which is going to give us X squared over 0.100 minus X. And then we try out the simplifying assumption, which is going to give us X squared over 0.100. And that gives an X value of what?
Is that K8 or K?
Oops. Ka. Ka. Don't round it. Was it 3 before rounding?
Yeah.
Oh, let's leave it. 7.93 times 10 to the negative 5. And so this is going to be 0.100 minus 0.1234793. 0, 0, 0, 0. So this is going to be 7, 0, 2, 9, 9, 9, 0. This is going to be 7.93 times 10 to the negative 5. 7.93 times 10 to the negative 5. All right. Then let's do the KB. Next. KB would be H2PO4 minus. You know, H2PO4 minus can collide with water to form hydronium, or could collide with water to form hydroxide. Colliding with water to form hydronium is more favorable because the Ka is bigger, but it can still collide with water to form hydroxide. And so this is going to form H3PO4 plus hydroxide. And so what should we do? Should we carry this down? Yeah, we should carry this down, huh? So let's go ahead and carry this down to step 2. Is that all we should carry down? Is that all we can carry down? Yeah. And so initial, we have 0.0999207 water. Then H3PO4, we assume nothing's happened. What about hydroxide? We'll assume no collisions have happened here, right? And so the change is going to be minus x plus x plus x. So at equilibrium 0.0999207 minus x molar, x molar, and x molar. And that Kb here is equal to the phosphoric acid concentration times the hydroxide ion concentration divided by the dihydrogen phosphate concentration. And so this is going to equal 1.4 times 10 to the minus 12, which is going to give us x squared over 0.0999202 minus x. We try the simplifying assumption here. So this is going to give us x squared over 0.0999202. And that means x is equal to, actually, do you see the simplifying assumption works here? No problem. I didn't even bother with the calculation because this is 10 minus 1 over 10 to the minus 5. I mean, 10 to the minus 5 over 10 to the minus 1 times 10 squared. It's going to be way less than 5%.
If we're not sure though, then we could do the calculation.
Yeah, you calculate it. And so what is x here?
1.39. Oh, wait,
It's
10 times 10 to the minus 3.74 times 10 to the minus 7? Okay.
1, 2, 3, 4, 5, 6, 7.
All right. So this is 0.0999207 minus, I need 6 zeros. 1, 2, 3, 4, 5, 6, 3, 7, 4. And so this is going to give me 6, 2, 3, 9, 2, 9, 9, 9, 0. Did it really make any impact here? No. That's good because we don't want it to perturb step 1, because if it perturbs step 1, then what does that mean? What? You have to do it all together, right? And so that's good. And then the phosphoric acid, 3.74 times 10 to the minus 7 molar. And the hydroxide, 3.74 times 10 to the minus 7 molar. Okay, now what do I do about the pH? Well, I need to do what next? I need to do what, KW, or combine these two? Look at, in step 1 I form hydronium. In step 2 I form hydroxide. Do they cancel each other out? Do they cancel each other out? Normally they would, but there's something missing, because if they cancel each other out, what's going to happen to the equilibria? Is it still going to be at equilibrium? Would that be a significant change in both the hydronium and the hydroxide? Well, it looks like I have excess hydronium, right? So I'm going to lose all my hydroxide. When hydronium and hydroxide combine, they form water, right? This has got a strong driving force because it's strong acid and strong base. And so if they cancel each other out, that's going to screw up both equilibria. But there's something of a disconnect, because if you don't see this, lots of people don't see this, but there's a big problem here. And the big problem here is that these two equilibria are connected, because hydronium and hydroxide are connected by Kw. So if hydronium is this concentration, then that fixes hydroxide at that concentration, and vice versa. Because the hydronium and hydroxide are on a seesaw. You can't disconnect them. What did we do when we solved this? We disconnected the hydronium and the hydroxide. The hydronium and hydroxide are tied together by Kw. You see that? And so, unfortunately, what a lot of people will do is they'll just cancel one or the other out, whatever the limiting reagent is. But that'll screw up the equilibria. And so these two equilibria are tied together. So that what that means is that I need to solve this using the, is it locked?